trend we're going to study is atomic radius. Now, you all must have studied what is radius in your geometry class. Is that right? All right? You must have studied what is radius. But you have to realize, are you on this slide? All right? So now, if you study radius, remember this is an electron cloud. What is it? It's an electron cloud. So cloud is almost like a fog. When you're driving through fog, do you know where the fog ends and where it's clear? Can you really say that? You can't. So similarly, it's very difficult to measure this distance from the center to the edge of the cloud. That's very hard to find. So how do they actually measure radius? They know this is the nucleus. They know this is the positive nucleus. They can deduct a positive nucleus with an instrument. Okay? They put two atoms as close as possible to each other. They take the distance between two nucleus and 1/2 of the distance between two nuclei is known as what? Is known as atomic radius. Does that make sense? They measure this length and then they half it. And that distance is what is known as the atomic radius for a given element. Do we understand this? Okay? Now, let's move on and let's see what is the pattern or the trend when it comes to atomic radius. What happens to atomic radius as you go down a group? It gets bigger. What happens to radius as you go across a period? It gets smaller. So now we're going to switch stop for a minute and we're going to go through this worksheet. So what kind of questions will you get asked on friends? Now that you know the pattern, I'm going to start with Edda at the end. So let me find that worksheet. Should I grab one from the door? So let me get one from the door. Oh wait, I actually have my answer right here. Okay. So now, between potassium and bromine, which has a larger atomic radius? Edda. Potassium is right here and bromine is right here. So which has a larger atomic radius? Potassium. Now, this is really visual for you. Is that right? But you won't get such a nice visual clue. Instead, what will you get? Ooh, why is it going backwards? Okay, so you'll get a periodic table like this. You should remember that atomic radius increases going down and decreases going across. Is that right? You'll only get a periodic table like this. Will that picture be drawn and you'll be asked a question? No. So Sion, let's move to the next one. Sodium and magnesium. Here is sodium, here is magnesium. Which do you think has a larger radius? Sion? Sodium or magnesium? Very good. Sodium does have a larger radius. Okay, moving on to Sophia. Sodium has a larger radius. So please circle that in your paper. Francium and fluorine. Sophia, here is francium, here is fluorine. Which do you think has a larger radius? Very good. Francium does have a larger radius. Okay. Moving on. Jessie Lee, lithium and calcium. So here is lithium, here is calcium. Which do you think has a larger radius? Going down.
Oh,
Calcium will be 3 circles, right? Much larger because of the added circles. Does that make sense? Okay. The next one, Mohammed. Iodine or bromine? Iodine is right here. Bromine is right here. Which has a larger radius? Larger radius. Which is bigger? Iodine. Do we understand this? Do we all understand how radius changes? Will we remember the pattern? Okay. The bigger question when it comes to trends is you will be asked to write. Okay? I will tell you this on your quiz or on your test. I will actually tell you what happens to atomic radius as you go down a group. It gets bigger. I will tell you it gets bigger, but I will ask you, why does the atomic radius get bigger as you go down a group? So Aiden, I'm giving it to you that it gets bigger. And I'm asking you the question, why? The new student should be able to write. How will you write the answer? In terms of the distance of the valence electron from the nucleus and in terms of the force of attraction. So Aiden, can you help me out here? Why does the atomic radius get bigger as you go down a group? Who wants to try this? Who wants to try? Sarah, you want to try? What happens? Why does the atomic radius increase as you go down a group? The distance of the valence electron from the nucleus are these the valence electrons? Yes or no? The distance of the valence electron from the nucleus increases and the force of attraction decreases and hence radius increases. Do you understand it? Does that make sense? The cloud gets bigger because the nucleus is not pulling it in closer because it's further away. Does that make sense? Okay, going back to Mustafa now. All right. So now as I go across, does my number of circles change? Not really, right? But what happens to the size? Size becomes smaller as you go across a period. These are called periods, right? You put a period at the end of a sentence. Those that are horizontally are called periods, correct? So the atomic radius becomes smaller as you go across a period. Why?
Because the number of protons increase in the force of attraction.
For the valence electron increases. Does that make sense? So they are getting added to the same energy level. Is that right? Are they getting added to the third? Or if you're moving across fourth, they're getting added to the fourth energy level. Is that right? They're getting added to almost the same distance from the nucleus. Is that right? But the number of protons in the nucleus increases. Hence, the force of attraction is stronger. As the force of attraction is stronger, what happens to its power to pull the electrons inside? That increases, and hence radius decreases. Are we good? You really need to write these things out. If you don't, you will not get any credit. So trends unit is all about being able to explain the why. Do we understand this? Okay. So we are good with picking atomic radius. Is that right? Now, let's go to the second block. All right. Circle which element has the largest radius. I would like you to look at uh, this example here. Maybe we will do chlorine, bromine, and sulfur. There are three now. Let's look at this question. It's asking us to compare the size of chlorine, bromine, and sulfur. Are we good? All right. Aiden, can you help me with this? Chlorine, bromine, and sulfur. I want you to order these elements. Now, this is not the same question that's being asked on that sheet. I'm going to ask you to order it in increasing atomic radius. What do I want to do? Increasing means what? Getting bigger. So, smallest to biggest. I want you to tell me among the three, which is the smallest in size, Aiden? This is a hard one. But when you go across, what happens to the size? So which will be smaller? Which will be the smallest? There is no chlorine. Huh? Well, we are in the... Well, I'm sorry, this is chlorine, right? This is sulfur, chlorine, and bromine. So chlorine is going to be the smallest. What do you think will be bigger than chlorine? Sulfur, and which will be the largest? Bromine will be the largest. Do you see that? You understand it? Okay. Let us do an easier one. Let us do, Keith, I'm on to you. Lithium, sodium, potassium. You're talking about size, Keith. You're talking about size. You're talking about the pattern. Do you know what radius means? Radius of a circle? Okay, I'll come back to you after Ms. McGrain is on to you. Nibbe, are you with me? All right. So tell me, which is the smallest, which is the biggest? Lithium, sodium, potassium, they're all down the group. Yeah. Which is the smallest? Which is the biggest? Yeah, which is it? Lithium, sodium, potassium. Lithium is the smallest, followed by what? Sodium, followed by potassium. So they ask you to order. Do you think you can do that? Increasing, decreasing? Read the question carefully. It's not enough if you know the pattern. They'll ask you to order it. And you should be able to do it. Are we good with atomic radius? So what type of questions can they ask? Which is bigger, which is smaller? Arrange them by increasing or decreasing size. And they can ask you the question, why? Does that make sense? All right. The next thing we are going to get into is, so the size is again given to you. The reason is given. All right. You can read up all your reasons and you should know how to explain. We are next on to ionization energy. Why should we learn ionization energy? Let's think about this. Okay? Now I need you to take out notebook paper and I need you to write with me. Take out notebook paper. This is stupid. We'll go back. Okay. Take out notebook paper and write with me.
No, not in your composition book, guys. All right, who needs paper? Anybody else need paper?
All right. So we're going to do the Bohr model for sodium. All right. So sodium, where is sodium on the periodic table? Is sodium a metal or a non-metal? No.
Sodium, Na, left.
All right, we should know this. We should know this in a periodic table. What are these? These are the metals. These are the non-metals. Where is sodium on your periodic table? Right there. Group 1. Is sodium a metal or a non-metal? Metal. All right. Now sodium is in period 3. Do you see that? Is sodium in period 3?
Yeah.
So how many, Keith, are you with us? You should need to stay with us. Sodium is in period 3. How many circles will I draw for the Bohr model for sodium? 3. All right. I need you drawing 3 circles for sodium. A neutral atom, Gabby, as I write, you write. Okay, so how many electrons does sodium have? How many total electrons if it's neutral? What is the atomic number on the periodic table? 11. How many will go in the first circle? 2. How many will go in the second circle? 8. It's not aligned properly, so it's troubling me. 1. 8 in the second circle, right? Let me do this again. All right? So 2 in the first circle, 8 in the second circle, right? So how many total have I accounted for? 2 plus 8. So how many will go in the outermost circle? 1. All right. Sodium is a metal. Sodium is a metal. What is the state of the substance? Is it a solid, liquid, or gas? It's a solid. It's a solid. Okay? And so if what will happen if you take sodium and drop it into a container with water? If you have water and you drop sodium in it, what will happen? It will explode.
Low. Because it's highly reactive.
It will explode. All right?
Ms.Geeta, didn't you show them that you...
Yeah, no, not yet,
Oh,
Mr.
okay.
Brain. All right? It will explode. Okay? Let's come to chlorine at this end. What is chlorine? Is it a metal or a non-metal, Gabby? Where did I write chlorine? Non-metal. All right? Chlorine is a non-metal.
Right, now we're doing chlorine.
And look at my periodic table. Look at my red, blue, and black. What color is chlorine on my periodic table? Red. Therefore, chlorine is a gas. What is chlorine? Chlorine is a gas. Now, what period is chlorine in? What period is chlorine in? Which period number? So how many circles will you draw for the Bohr model? 3. How many total electrons does chlorine have? 17. How will I draw? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. How many valence electrons does sodium have? Valence electron does sodium have? How many valence electrons? 1. How many valence electrons does chlorine have? 7. Electrons in the outermost energy level are known as valence electrons. Yes or no?
Yes.
Okay. So now, have you ever smelled chlorine gas? Like, have you gone to swimming pools? Do they add chlorine gas? It is a gas, all right? It's a greenish yellow colored gas. Greenish yellow colored gas. If you smell chlorine, say you want it looks green, it looks cool. If you go and smell the gas, what will happen? You'll start coughing. When was it used, Miss McGrain?
When was it used, Neve? I just told you. World War I, mustard gas. You all remember studying that in history? Yeah. Highly poisonous. Lethal. They don't use it anymore. You don't think. Pardon? Why do they use it in pools? Good question. What do you think? Pardon? To kill children? No. Good question, Ms.Geeta. They want to know why is it used in swimming pools? Well, we have the concentration is different for starters, right? And it also helps.
All right. Let's see.
All right, we're going to look at this.
I don't know how long this video is.
It's a short one. Ooh,
This is I can't find the shorter one that I had earlier on.
So Lonnie's filled a beaker with elemental chlorine. That's chlorine gas, Cl2. It's a yellow gas. He'll also use solid sodium metal. Solid sodium metal is a shiny silver metal that's very soft. You can actually cut it with a knife. Sodium metal is very reactive. It will react in air and water, so it's stored under hexane. He'll pull off a small chunk and immediately store it under hexane while he prepares the rest of the experiment. Now, to get the reaction to go, he'll want to clean the sodium, make the surface very clean, and warm it slightly to help the reaction proceed. He'll do that by placing the sodium in a spatula and then warming it over a flame to clean the surface and to get the sodium warm enough to initiate the chemical reaction. Now, the reaction between sodium metal and chlorine gas proceeds, but we know the ionization energy of sodium is greater than the energy released, the electron affinity, when chlorine accepts electrons. So the reaction goes because the positive ions formed on sodium and the negative ions formed on chlorine are drawn together, a Coulombic interaction, to form an ionic bond. The formation of that ionic bond, plus and minus charges attracted together, releases energy, and that's the driving force for this chemical reaction. And you can see that it's exothermic. Energy's being released. Bright red glow, typical of emissions from sodium. Now, the reaction between sodium and chlorine, of course, forms sodium chloride. We typically know that as table salt. And Lonnie's prepared some in advance. He has white table salt, purified, that he can show us.
What is all the protective safety?
See, this is all.
There it is, purified in advance from Lonnie Laboratories. And Lonnie tells me the salt that he makes in Lonnie Laboratories is far superior to any salt that you can buy in the store. So what does he have to do now?
Himalayan salt.
Ah, Lonnie's going to demonstrate, clearly hasn't had his breakfast this morning, that
Okay, that is not
Lonnie
right
Lab
now. I
salt
don't want to show that.
far superior.
All right. So,
Sit on hard-boiled
okay. So, what did they just do? So, this was the reaction that was happening between the metal sodium, which is squishy, and that's why it's stored under hexane, and the chlorine gas that was in the tall jar. Is that right? Now, this is dangerous to health. This will explode. This is a metal, all right? It's solid. You can't use it as it is. Did he heat it up in a spoon?
Yeah.
What was happening was the sodium is now converted to a gas in the process. All right? It starts to evaporate. Does that make sense? As you heat it up, it starts to evaporate, and then you have an atom of sodium. Now, will sodium lose an electron or gain an electron? Gain 7 electrons. What will sodium like to do? Lose. So what happens is
Right?
this electron, and chlorine has 7. It desperately wants 1. Yes or no? So sodium now loses its electron and becomes the sodium ion, which has how many electrons in its outermost shell? 8. Do you agree? Do you see that? Right? And what happens to the size as it loses the electron? It gets smaller. All right? It becomes Na plus. What happens to chlorine as it gains the electron? What will happen if you sit in a circle and you want to accommodate another person? It gets bigger. All right? So chlorine now gets bigger than the original size, and chlorine now has how many in its outermost shell? It has 8 in its outermost shell. And by gaining an electron, what has chlorine become? Chlorine minus. So there is a strong force of attraction, right? What is this? There is a strong force of attraction. And what is this substance known as? This is your salt. Can you eat salt? Yes. So now, in this process, have you removed an electron from sodium? Have you removed an electron? Right? Yes or no?
Yes.
This energy to remove, are you making it an ion? Are you making it an ion? Yes or no? What are ions? What are ions? What are ions? They are atoms that have lost or gained an which particle? Electron. So, this energy that you require, now this requires energy. You just cannot pull away an electron. Why? Isn't the nucleus attracting this electron? Yes or no? Isn't the nucleus pulling it and keeping it together? So you require energy. Energy required to remove the electron. To remove the electron is known as what? Is known as ionization energy. What is this energy known as? Ionization energy. That is the next trend we are going to study about. Does that make sense? Do you understand what is ionization energy? Energy required to remove an electron from an atom in the gas state. Now, there is another energy here. Here, electron is being added. Is that right? We don't do this at the Chem 1 level, but I'll be doing with my honors. This class is a very bright class. I'm going to go on and teach you that. Energy is actually released. Energy is released when electron is added. Alright? And that is known as electron affinity. What is that known as? Electron affinity. So when you want to say or predict, hey, will this reaction happen? If I take one element from the periodic table and another element from the periodic table, I put them together, do I actually have to carry on the reaction? Not really. If I know my ionization energy, my electron affinity, and all those values, I can actually, with doing math, I can predict if the reaction will happen or not. Does that make sense? Do you understand it? That's why we study these patterns. We have this notes page done. All right? We're going to move on and go back to ionization energy. All right? What is ionization energy? Energy required to remove an electron. Very good. I love that kids are able to say before I teach this. All right? Ionization energy is the energy required to remove an electron from an individual atom in the gas state. Does everybody understand that? Now, we need to not just study what is ionization energy, guys. Make sure you know how to define ionization energy. You will get asked definitions. Is that clear? Okay? Now, what you need to know is what is the pattern in ionization energy. Now, let me ask the class. In which case, is the nucleus pulling strongly or weakly here? Jackie, as the distance increases, what happens to the force of attraction? Decreases. So is the nuclear pull strong or weak here? Weak. How about here? It's strong. In which case will you require more energy to pull the electron? When the nucleus is pulling strongly or when it's pulling weakly? You need more energy? When it's hardly holding it, do you need more energy to pull it out? Or when it's strongly pulling it, do you need more energy to pull it out? Which case? Here, let me show this. Evelyn, you are the nucleus, all right? Pull. If somebody wants to whisk me away, and Evelyn is just like weakly holding me, I'm far away, she's not even noticing me. Is it easier to whisk me away? But when I'm really, really close to Evelyn, hold me very tightly. Hold on tightly to it, Evelyn. All right? When she's holding and I'm very close to her, do you think it's possible to remove me from her? So remember, thanks. Smaller the size, more energy is required. Bigger the size, less energy is required. Do you understand why? All right? So ionization energy is more up top when the size is smaller. Ionization energy is less down below. Is that right? So what happens to ionization energy as you move down a group? It decreases. What do you think will happen as you go across, as it gets smaller and smaller? What will happen to ionization energy? The energy required to pull the electron out. As it gets smaller and smaller, what happens to ionization energy? Do you require more energy or less energy? More or less? As it gets smaller. As it gets smaller, do you need more or less? Okay, bigger the size, what is your ionization energy? Bigger size, less energy. Do you agree? Smaller size, more energy. Do you agree? So what is your ionization energy trend as you move across? It gets smaller and smaller. What is the pattern? So the energy gets higher. So ionization energy increases as you go across a period. Does it make sense? So you need more energy to remove as you go across. You need less energy as you go down. Does it make sense? Okay? So let's go to this sheet of paper now. Who's the kid who answered last? I think Utaka needs to answer now. Utaka, between potassium and bromine, let's see, ionization energy, these are the factors. I need a periodic table somewhere. This is electronegativity. Let's go back to this periodic table. Maybe I'll use this periodic table again. All right? Just helps me. Ionization energy trend. Okay. So Utaka, are you on 3? Utaka, which has larger ionization energy? Potassium or bromine? In which case do you need more energy to pull the electron out? In case of potassium or bromine? Which is bigger in size, which is smaller in size between potassium and bromine? What is the pattern in size?
Smaller the size, more energy.
So which is smaller, potassium or bromine? Potassium is right here. What happens to sizes? Bromine is smaller in size, therefore which requires more energy? Bromine requires more energy, right? So will bromine have higher ionization energy? Do you agree? All right. Marvi, sodium or potassium, which will require more energy? Gabby, you need to be thinking actively. Be stay in class. Think. Yes. Sodium is smaller, therefore sodium requires more ionization energy. Is that right? Do you agree? Jackie, francium or fluorine, which requires more energy? Francium or fluorine? More energy. Fluorine requires more energy. That is correct. Maya, lithium or calcium, which requires more energy? Lithium or calcium? Which requires more energy? Lithium or calcium requires more energy. Lithium requires more energy. That is correct. Hey, iodine or bromine, which requires more energy? Bromine requires more energy. That is correct. All right. Crystal, we are now going to a group of 3. We're going to question number 4, and I'm going to ask you, I'm going down to the second one, sodium, magnesium, and potassium. Tell me which has the most, which has the least. Which will be the most, which will be the least. Magnesium is the most, very good, because it's the smallest. Potassium has the least, so what will fall in between? Sodium. Do you see that? All right? So, well, actually, ionization energy trend is opposite, right? Potassium is less than sodium, less than magnesium. You require most energy here. Yes or no? Do you agree?
Yes.
Magnesium requires most energy. Potassium requires least energy. Do we understand what is ionization energy and what is the pattern in ionization energy? Do we all understand it? Okay. The next thing we need to know is electronegativity. Okay. Now, electronegativity. Now, in all cases, so you're looking at the periodic table and finding out which will require more, which will require less. Is that right? We studied which trend? Radius. We studied ionization energy. Now, sometimes you will take elements like phosphorus and chlorine, or you will take tin and iodine, and they are already bonded to each other. What is it? They're already bonded. So let's take, say, phosphorus and chlorine. All right? Not in all cases is one completely giving and one completely taking. In some cases, there is also sharing of electrons. Okay? So there is a pair of electrons. What are these? These are a pair of electrons, that are being shared. What is it? Electrons being shared. ING, shared. All right? But the problem is they are not equally shared. All right? They're not equally shared. Not equally shared. What happens is, so this is in a bond. What is this? This is a, they've already come together and they are bonded. It's like a couple coming together and they are in a marriage. They're already bonded. All right? But who has more control in a marriage? Is it the man or the woman? Or between homosexuals, whatever it is, you know? Now, the question is, between elements, which will have more pull of the electron pair. Now let's think about the size. Which do you think will have more control? A smaller atom or a bigger atom? Think. In which case is it closer to the nucleus? When it's smaller or when it's bigger? When it's smaller, it's closer to the nucleus. When it's closer to the nucleus, what happens to the force of attraction? It distance, well, this is the opposite now, right? As the distance decreases, what happens to the force of attraction? Increases. So which will pull more? The smaller one will pull the electron pair more. The electron will be distributed closer to the smaller atom. Does it make sense? Do you understand it? So, electronegativity is defined as they are pulling. Let's assume this is a couple. All right? Which will pull more? The smaller one will pull more. Do you understand? And electronegativity always pertains to a bonded situation. They don't talk about a single atom, but now that they're bonded, which has more control? Does that make sense? Do you understand the definition of what is electronegativity? Now we have to study the pattern. Is that right? The pattern is very obvious to us. Smaller the size, what happens to electronegativity? It increases. Bigger the size, what happens to electronegativity? It decreases. So we are now on to crystal. Let's go to the back. All right? Let's go to the back. Let's see which one will pull more. Let's see, crystal. Is it going to be potassium or bromine? They're in the same group. Bromine, because bromine is the smaller in size, right? Ian, sodium or magnesium, which will pull more? Sodium or magnesium, which will pull more? Magnesium will pull more because it is smaller in size. Do you see the height refers to the electronegativity in this chart? Are you able to see that? The taller it is, the more electronegative it is. Does that make sense? This is a 3D chart. So Karen, We are now between francium, it's not even listed here. So here is francium, here is fluorine. Which will pull more? Karen? Fluorine, because it's the most electronegative element on the periodic table. Now, can you go down to the next set? Can you go to question number 6? Stephen, we are comparing chlorine, bromine, and sulfur. Which is the most electronegative, which is the least electronegative among the three? Which is the most, which is the least?
Sulfur is the most.
Well, as you go across, what happens to the size between sulfur and chlorine? Which is smaller in size? Sulfur and chlorine, which is smaller? They're in the same period. What happens as you go across, Stephen? Sulfur and chlorine are in the same period. What happens to the size between sulfur and chlorine? What happens to the size between sulfur and chlorine? Don't you get smaller as you go across? Right? No. Didn't I draw this?
Oh, left or right?
Yes. So which will be the most electronegative, Stephen?
So
Which is the smallest in size? In fact, look at the height. In the heights, give that away. Which is the most electronegative?
alright, the most.
The most. Yeah? You're lost because you're lost at size. You're getting confused with size. I can see you're completely lost. Alright? Chlorine is the smallest. Chlorine will be the most electronegative. Is that right? Between sulfur and bromine, which is smaller in size? It'll be sulfur and then bromine. Is that right? But actually this one shows bromine is slightly higher than sulfur. Is that right? It shows bromine and then sulfur. Is that right? Is that the order? Do you see that? Okay. Now, I need you to stay focused. Let's do another one. Let's do a group of 3. That's actually easier. And Stephen, you're still going to help me because you're so lost. Lithium, beryllium, boron. Which has the most electronegativity? Boron is the most, followed by Be. Well, it's actually, yes, more, this is less than, right? Because boron is the most, beryllium is next, followed by lithium. Lithium is the least electronegative. Yes or no? Okay. I need you to write down an example now. I need you to write an example now. Alright? All of you, let's look at sulfur, chlorine, and what is the element after chlorine? Argon. They are all in the same period. Do you see that? I need all of you to pay attention. This is a tricky question. This is a really tricky question. Okay? This contains a noble gas. What is this? It contains a noble gas. Do you think noble gases take part in bond formation? No. Noble gases do not form bonds. Write that down. Noble gases do not form bonds. Write that down. So do they have electronegativity? Their electronegativity values equals 0. For noble gases, the electronegativity value equals 0. Are we writing this down, Aiden? This is very important for us to know. I will test you on this. Now, I'm asking you to arrange from the least to the most. Even though they run across a period and it increases going across, can I choose this to be the most electronegative element? That's just wrong because it's a noble gas. So, argon will be less than, it is the least among all the elements in a periodic table. Is that right? Followed by sulfur, followed by chlorine. That will be my order if you have a noble gas. Shall we do one more example? Shall we do selenium, bromine, and krypton? Which will be the least? Selenium, bromine, and krypton. Which will be the least? Krypton is the least, followed by what? Selenium, followed by bromine. Do we understand it? Do we understand if they include a noble gas? Please, it is zero. Even though it's the end, it is zero in a periodic table. Do you understand this? Okay. So we studied three patterns. We studied size, we studied ionization energy, and we studied electronegativity, which is in a bond. Do we understand this? The next thing we need to know is, shielding effect, octet rule. What is octet rule? Underneath octet rule, I want you to draw a periodic table. Underneath octet rule, I need you to draw a periodic table. What are these? Metals. What are these? Non-metals. Metals like to lose or gain. Metals like to lose electrons. Metals are losers. Metals like to lose electrons. What will they become if they lose electrons? What do they become if they lose electrons? They become cations. Non-metals like to gain electrons. What do they become after they gain electrons? They become anions, right? And metals become cations. All elements want to lose or gain to have how many in their outermost shell? How many do they want to have? 8. What does the word oct mean? Octopus, octahedron. What does it mean? Oct means 8. Octet rule. All elements want to lose or gain to have 8 valence electrons. Is that right? Metals lose electrons and become cations. Non-metals gain and become anions. Do we understand this? Okay. The next thing we need to know is, what is shielding effect? What is the shield? It protects. Is that right? Let us understand shielding effect. Now, let's say this is the nucleus. Okay? There is the first core, there are electrons, right? In the first energy level, there are electrons that are whizzing around. Is that right? In the second energy level, there are more electrons. The third energy level, there are electrons. Is that right? Now, you have a valence electron. What do you have? That is your valence electron. What are these? These are your core electrons. What are these? These are your core electrons. Write that down. They're core electrons. Okay? Now, this is almost like how Mr. Hain teaches his students. Alright? I'm trying to hit on a girl who's all the way in the back of the bar. Okay? But there are girls in between that I'm not interested in. Do you think I will be able to attract that girl who's all the way far if I do some gestures and try to attract her? She probably will not understand it. Is that right? So, if there are core electrons, do you think this nucleus can attract this valence electron? It doesn't become harder? Yes or no? Each layer of electrons acts as a shield. Does that make sense? And what does the shield do? Prevents the nucleus from attracting valence electron. Yes or no? Does that make sense? Do you understand it? Okay? So now, let's see what is the pattern in shielding. So I have my really strong nucleus. I'm going down a group, all right? There is just one layer of core electron and there is a valence electron. If I go down to group 2, there's 2 layers. The flag of United States of America.